We're going to do some example problems now, applying what we have learned about Gibbs free energy. The first one comes from page 852 of your textbook. It says, calculate the entropy of vaporization for acetone at its normal boiling point. And normal boiling point simply means the boiling point at atmospheric pressure, which is the normal pressure. And we're given two temperatures. I'm assuming that the lower temperature is the freezing temperature of acetone, and the higher temperature is the boiling point. And just a review, because we're in this chapter on energy, if we made a graph and the x-axis has increasing amount of energy added to the system, and on the y-axis we have temperature in degrees Celsius, and then if we were to make a temperature versus energy graph for acetone, it would melt at negative 94.8 degrees Celsius. Then if you continue to add energy, it would heat up until it gets to a temperature of 56.1 degrees Celsius, and that's the point at which it would evaporate. And eventually, if it all evaporated, you could see the temperature rise again. Now, we need to think about a couple of things that we have learned. First, knowing that we are at the boiling point, that tells us something about the change in entropy of the universe, which also in turn tells us something about the Gibbs free energy of this process. Thinking back to our earlier notes when we were looking at the data for water at different temperatures and the change in entropy of the system and the change in entropy of the surroundings. The boiling point of water we know to be 100 degrees, and right around that point, that is the point where the change in entropy of the universe was zero, which also would mean that the Gibbs free energy would be zero. And I did mention also earlier in the notes that zero implies equilibrium. We're really going to get into what equilibrium means in another month, but it is true that when something is boiling, there is an equilibrium happening, which means that some water is evaporating and some water is condensing. But if we just think even back to the data we've looked at today, we know that the change in Gibbs free energy and the change in the entropy of the universe is zero when something is boiling. We just learned that Gibbs free energy is defined as the enthalpy change minus temperature times the entropy change. And we know we've got two entropies here, heat of fusion and heat of vaporization. But since we want to figure out the entropy of vaporization, we're going to pair that with the enthalpy of vaporization. So we're going to use 29.1 here. The change in Gibbs free energy is zero. And well, we've got to use the temperature. We're at the boiling point, so we want to use the boiling point or the boiling temperature here, but we have to use it in Kelvin. Again, this equation is not hard to use, but the devil's in the details. You've got to think about joules versus kilojoules. You've got to always use Kelvin. Those are the things that get people when we're doing these calculations. So this will be 56.1 plus 273. Times this will be the entropy of vaporization, what we're looking for. Now it's a matter of doing some algebra to solve for delta S vaporization. So negative 29.1 divided by negative, this would be 329.1. Delta S of vaporization, that becomes positive. And when I divide those, I get delta S of vaporization is equal to 0.0884. And the units right now would be kilojoules because this was in kilojoules. So notice when I calculate entropy and I try and put it in kilojoules, you get a very small number. That's why it's usually tabulated in joules instead. So it's kilojoules divided by mole times Kelvin. Typically, this is probably, as I said, entropy is usually expressed in joules. So you would probably see it as 88.4 joules per mole of reaction times Kelvin. So then I have this follow-up question here. Does the sign of the entropy change of the system make sense? I saw people make mistakes like this on the quiz. It's always good to go back and just give yourself a sanity check. What happened here? Okay, so we're talking entropy. Entropy is about the number of possible ways to store energy in a system. The process that just happened is that we took liquid acetone and we evaporated it. Well, a gas has a lot more possibilities for how its particles can move, how fast or slow they are. They have a lot more freedom to move around and be in different places. So that means that there are going to be many, many more possibilities for how to store energy, how to distribute energy in our system. Therefore, it should make sense that going from a liquid to a gas, the entropy is going to increase. That means that it should make perfect sense. I should be expecting to have a positive delta S, or an increase in entropy in this problem. So yes, the sign of the entropy change makes a lot of sense. You can do this with enthalpy problems too. If you get a delta H, a heat of reaction, an enthalpy change, and you get to the end, it's always a good idea to say, does it make sense? Was I expecting an endothermic change and I have a positive number? Was I expecting an exothermic process and I have a negative number? Does that match the descriptions in the problem? Great mental check to do with yourself. Okay, now we're going to look at another example problem. This example problem came from your textbook, page 864. This says calculate the heat of reaction, and we're given a reaction to do this for, and we want to know, is the reaction spontaneous at 25 degrees? Is the reaction spontaneous at negative 55 degrees? So there's a couple of ways to do this problem, but since it's asking me questions about specific temperatures, and not just 25 degrees, I'm going to assume that the enthalpy of reaction and the entropy of this reaction are relatively constant at different temperatures, and I'm going to employ this definition of Gibbs free energy here. Delta G equals delta H minus T delta S. And I might think, well, I don't have delta H of reaction, and I also don't have delta S of reaction. However, either if it's an AP problem, they will probably give you a table with some information to help you figure that out. Or in the case of our textbook, we have the heats of formation and the entropy is all tabulated in the back of the textbook. So before we can use this reaction, we are going to have to figure those things out. So we'll start with the delta H work. So for delta H, the heat of formation for NO is 91.3 kilojoules per mole. For O2, well, that is an element, so the heat of formation is defined as 0. For NO2, the heat of formation for NO2 gas is 33.2 kilojoules per mole. So these are the heats of formation that I looked up in Appendix 2 in the back of my textbook. So heat of reaction is products minus reactants, and I have to take into account coefficients. So it'll be 33.2, that's our product, minus 91.3, and in this case there's no coefficients because those both have coefficients of 1. So I got that the heat of reaction would be negative 58.1 kilojoules per mole of reaction. And I'm going to do the same thing for the entropies. The entropy for NO is 210.8 joules per mole Kelvin. For oxygen, it is 205.2. And for NO2, it is 240.1. Again, I just looked all of those up in my textbook. So the entropy change for this reaction is products minus reactants. So 240.1 minus 210.8 minus, now I do have a coefficient here to worry about. The oxygen is a coefficient of 1/2. So minus 1/2 times 205.2. So I figured out that the entropy change for this reaction is negative 73.3 joules per mole Kelvin. I can do the mental check here and say, hey, I started out with 1.5 moles of gas and I only have 1 at the end. So less moles of gas, less possible ways to distribute energy because there's just less particles floating around, and that makes sense that I got a decrease in entropy for this reaction. So now I have the heat of reaction, I have the change in entropy for the reaction. I'm going to put those two things together and try and figure out Gibbs free energy. We're asking, is it spontaneous at 25 degrees? Is it spontaneous at negative 55? We'll do 25 first. So negative, and I have to make units match. This is one of the two biggest things to mess up. Notice we got joules, kilojoules. I'm going to change this from 58.1 to 58,100 minus, and temperature has to be in Kelvin. So instead of 25, I'm going to use 298 Kelvin times the entropy of reaction, which is negative 73.3. So if I add those two up, I get negative 363,000 joules per mole Kelvin. I want to write two reminders to myself here, both in joules. We got to make the units match, and the temperature is in Kelvin. Watch the details. All right, now we can answer the question, is the reaction spontaneous? Negative delta G indicates a spontaneous reaction, and actually means there's extra energy left over that you can do something else with. And we would say that this reaction is driven by enthalpy. So if I look at the two terms here, we've got the delta H term and the delta S term. The delta H term is negative. The delta S term is negative times negative, which is positive. So if I think about what's driving this reaction to happen, it's the fact that we have lots of extra heat available to make the universe more disordered and more entropy, the surroundings of our system. This would, a negative, we're trying to say like what part of the reaction contributes to Gibbs free energy being negative. Well, if this is positive, it's not contributing to the spontaneity of the reaction, while this term being negative is. So we would say that this reaction is driven, the spontaneity is driven by enthalpy, because it's the enthalpy term making the reaction spontaneous. Now, we're also asked, would this be spontaneous at negative 55 degrees Celsius? So we're going to do the same calculation, but instead of 298 Kelvin, we're going to use 218 Kelvin. So I'll give myself a little bit more room, and we're going to do this again, but this time for negative 55 degrees. Delta G is equal to, we're assuming that the heat of reaction is not majorly temperature dependent. The temperature now is going to be 218, that's 273 minus 55. I'm going to assume the entropy of reaction is not hugely temperature dependent. And so I get negative 421,000 joules per mole Kelvin. Notice we still have a negative Gibbs free energy, so this would be also spontaneous. And it would still be driven by enthalpy, because the enthalpy term is the one that's causing Gibbs free energy to be negative. The last thing we'll end with is, I keep saying Gibbs free energy, like if it's negative, it means there's extra energy left over to do something else with besides cause the process to be spontaneous. So we've been saying that as long as the entropy of the entire universe increases, that process will be spontaneous. And the entropy of the universe is determined by the system and by the surroundings. Even if the system becomes less disordered, has less ways to store energy, is a decrease in entropy, the overall process can be spontaneous as long as the enthalpy of the system is negative. That means that energy exits the system, and enough energy exits the system that the surroundings increase in entropy and kind of overcome the fact that the system decreased in energy. So if enough energy exits the system to make the surroundings more disordered and have a higher entropy, as long as the delta S of surroundings change is bigger than the change in entropy of the system, then the overall entropy of the universe goes up and the process is spontaneous. So Gibbs free energy is really a measure of extra entropy of the system that goes out that's not needed to compensate for the decrease in entropy of the system. So the system is becoming less disordered. It's being compensated for because the surroundings are becoming more disordered, but anything that's left over, not needed to make the system more disordered, can be used to do something else, such as drive another reaction to be spontaneous. So the example that comes up is actually a biology example. So, and Gibbs free energy, by the way, is a big topic in AP Bio. So this here is the process of storing energy in ATP. So adenosine diphosphate plus phosphoric acid makes adenosine triphosphate with water. Well, the Gibbs free energy for this reaction is positive 31. So this is something like normally ATP does not form by just hanging out. It is not spontaneous. However, in your body, we know that this happens. We know our bodies make ATP. Well, how does it happen? You do it by coupling that reaction, having it happen in the same place at the same time with the reaction of glucose with oxygen, which I think is called respiration. Yes, I was right. I remembered something from biology. This is glucose, and when your body processes glucose in the presence of oxygen, which we're breathing in, respiration, we breathe out carbon dioxide, and we also generate water. That reaction has a huge negative Gibbs free energy. All of that energy, that process is spontaneous, and it gives off a lot of extra energy that it doesn't need, like that can go out to the surroundings, and it isn't needed to make the surroundings more higher entropy, not needed. So if we pair these two reactions together, it will force this extra energy can be used to force this reaction to actually happen, to be spontaneous. So our body takes advantage of this a lot of times to make non-spontaneous reactions happen. That's why we call it Gibbs free energy. It's energy that can be used to do some other work. And that wraps up the examples for this chapter. But now it's your turn to do some practice both in class and on your homework.